Hello, everyone. Welcome to the DI101 Webinar Series. My name is Jared Evans, and I manage all of the marketing efforts for Distribution International. This series took a little break, but we are excited to get it back going, especially during these slow and challenging times. Before we get started, I just want to say on behalf of everyone at Distribution International, we as a family and as an industry are all in this together. We're committed to working closely with our customers and suppliers as a team to come out of this as strong as ever, and in some ways even stronger. So we'll get through this by pulling together. If you are not familiar with this webinar series, it is an incredible resource offered to DI customers, partners, and associates by partnering with our manufacturers and our industry experts. These webinars deliver informative presentations about industry trends, new technology, new products, and product applications. We're extremely excited to welcome our strategic manufacturing partner, Owens Corning, for today's webinar presentation. Distribution International is proud to welcome Doug Fast, a professional engineer and technical leader for Owens Corning. Doug is going to give a practical guide for industrial sound control. Doug is a professional engineer and technical leader for Owens Corning's industrial mineral wool product offerings. He has more than 20 years of experience in the insulation material industry, working in product testing, technical services, and new product development. He has a working knowledge of materials such as foam plastics, fiberglass, and mineral wool, as well as other traditional high-temperature insulations. Doug has contributed to the industrial insulation industry through participation with ASTM, as well as technical education in the form of blogs, webinars related to topics such as acoustics, corrosion under insulation, and personal protection. We're proud to have Owens Corning present today, and we thank them for their time. We will field questions at the end of the webinar. To submit questions, please use the Questions tab on the GoToWebinar panel. You can submit your questions at any point during the webinar, and we will answer all the questions during that question period at the end. We will also, at the end, draw for the winner of the Amazon gift card. So we will do that at the very end of the webinar. Without further delay, I will turn this over to Doug Fast with Owens Corning. Doug?
Thank you, Jared. First of all, welcome everybody, and I hope everybody is safe and well that's on the call, and hopefully everybody, your friends, family, and loved ones are being safe in these challenging times. First off, I'd like to say thank you to Distribution International for the opportunity to present this afternoon. Again, they're a great strategic partner. We're happy to support Distribution International, as well as those of you listening for any of your product or technical needs. Next slide, please. So what we're going to start off with today is we'll talk a little bit about the Owens Corning product offering with regard to industrial mineral wool, as well as our foam glass offering. And foam glass won't be emphasized in this presentation. However, we do have some assemblies towards the end where foam glass is going to come into play. The meat of what we're going to talk about today is industrial acoustics. And so a lot of you have probably already seen some of these terms, but we're just going to go through the background and cover some basics to make sure that everybody has a context or a framework to kind of look at some of these things. We're going to talk about NRC, or noise reduction coefficients, and that's really has to do with absorption of materials. We're going to talk about STC, or sound transmission class, which you normally wouldn't associate with industrial applications, but it'll make sense as we cover that, but it's really more about sound transmitting through something. And then we're going to talk about insertion loss, and that's really kind of the core of industrial piping insulation. Insertion loss you can think of as inserting a material to reduce the sound that's getting into an ambient space, and we'll of course cover that. And then finally, we'll talk about the ISO 15665 standard, which is being referenced within industry, and what those requirements are. Next slide, please. So before we get started, I have to give a word from our sponsor, of course, Owens Corning. Just a little background. We're a $7.2 billion in sales company as of 2019, employing 19,000 employees in 33 countries around the world. And we've been a Fortune 500 company for 65 consecutive years. And of course, serving residential insulation and residential roofing, commercial insulation applications, as well as industrial and composites. Next slide, please. And one final thing is, as Owens Corning, we're global in scale and human in scope. Now, just to talk a little bit about our product offering, just going from left to right. We start with our Thermofiber Pro section, which is competitive with a lot of the other mineral wool fiber insulations that are out there. We have the advantage of having water resistant, which is becoming more of a requirement within industry. But we also offer the product in a 4-foot section for productivity and also fewer gaps over length of piping. It also can result in less waste. These are typically used for combined cycle power facilities as well as refineries. Next, we have our Thermofiber industrial board, available in densities ranging from 4 to 15 pounds. Those are great for flat work, such as boilers or coal-fired power plants. They work both good for thermal, acoustics, in some cases even fire type applications. And then finally, on the right-hand side, we have our Thermofiber industrial wrap. And it, like our Thermofiber Pro section, is an acoustic product as well as a thermal product. We offer that in 3 different thicknesses, and that product is ideal for large diameter tanks and vessels where it's either too large or too cumbersome to try and use a pipe section or a quad or something like that to insulate it. Either way, we have a product that will meet your needs. Next slide, please. So when we talk about industrial acoustics, the first question that comes to mind is, why is this something that we should care about or pay attention to? One of the challenges in the facilities, we always want to keep the workers safe within the facility, and that includes keeping things quiet. As long as we can keep the overall sound level below 85 decibels, we don't have to require hearing protection for the people that work there. And then there's been a strong correlation between noise fatigue and, of course, loud places. And so we want to keep those as quiet as possible. Of course, the side benefit is the more insulation we have, the better we're insulating things thermally, so we're keeping more energy within the system. But anyway, the first thing is for work protection. The second thing is with a lot of the natural gas production going on, we have a lot of compressor stations that have really high noise levels. So we always have to be concerned with what's the noise at the property line going to be. We tend to build homes right on the property line of these noisy places. So not only do we want to try and insulate the equipment that the sound is radiating from, but also if we have compressor stations, we want to make sure we're insulating those walls well, so we're, again, not transmitting excessive noise to the property line. And then finally, it's always interesting that we never have time to do something right, but we always have time to do it over. I think one thing to keep in mind is that we always want to look at sound control before we have to go back and try and abate it. So we want to design that into the system. And it's not as expensive or complicated as one might think it would be. So it's pretty easy to do at the planning stage. Next slide, please. So just to give a little bit of background, whenever we talk about sound control, the first thing we talk about, and this is the top center portion where we talk about sound pressure levels, and this is about how loud something is. And we all get that. We've been around, a jet taking off or loud rock band, or been in a quiet neighborhood, so we have an idea what that spectrum looks like. And we see up above that it can range anywhere from 10 decibels to the threshold of hearing, all the way up to 120 decibels, which is an airplane taking off, a passenger jet. The other thing that we don't always think about, in the lower left-hand corner, you look at sound spectrums for equipment. And, a lot of times this is the type of noise. So sometimes you might have a low rumble, which is a structure-borne noise, and that's something you actually feel vibrating maybe through your feet if you're in a house that's vibrating, like if you're in an earthquake, or if you've ever been around drag racing where you can actually feel the compression against your chest. That's low-frequency sound. High-frequency sound tends to be that hissy type of sound. I always think of it at the ballroom at McDonald's or the playroom, where you hear a lot of kids screeching and screaming. That's high-pitched noise, and of course, we don't like that either. Pretty much any unwanted sound is what we call noise. Just to kind of calibrate on that, most human speech is usually between 2,000 and 2,500 hertz, to give us an idea where that sits. Finally, in the lower right-hand corner, and this is more of a subjective and objective kind of analysis or feel of how sound works. So as an example, if we perceive something as being twice as loud or half as loud, that's going to be plus or minus 10 decibels. If it's just barely noticeable, then that's going to be plus or minus 3 decibels, roughly. And of course, if it's going to be much louder or much quieter, then that's usually plus or minus 10 decibels. And again, it's very subjective, but it's something that has been quantified, and that's kind of generally where the guidelines go. Okay, next slide, please. So first off, we talk about noise reduction coefficients, and for those of you that have seen data sheets for mineral wool or fiberglass board products, you'll see those small fractions that are on there, and they have different frequencies. And of course, we'll look closer at that at the next slide. But how we test for how well something absorbs sound is we take a reverberation room, which we see on the left-hand side, and we turn the sound on to 100 decibels, and what they call a pink noise spectrum. So that means 100 decibels at every frequency, going from 100 hertz all the way up to 5,000, 8,000 hertz. And then you turn the sound off. And if you look at that small box in the lower left-hand image, you can see we have a reverberation time, and that's how long it takes for that sound level to go from 100 decibels all the way back down to the background level. So that's going to be kind of our baseline or our empty room. And that's a bunch of hard, flat surfaces where sound is very reflective. So what we'll do is we'll repeat the same exercise, but what we're going to do is put a sample in this room, and we're going to do the same thing. And what we see is we have a shortened reverberation time, and so that material is what caused that reduction in that reverberation time. So applying it to some math that's in an ASTM standard, ASTM C423, we can determine what the sound absorption is of a given material. And so the NRC value, again, we get data going from 100 hertz all the way up to 5,000 hertz, but we like to compare things with a single number whenever we possibly can. So what we'll do is we'll average the NRC value at 250, 500,000, and 2,000 hertz, and that average is what our NRC value is. And next slide, please. And next slide, please. And so just to give you an idea, I'm just looking at some of these plots, and let's look at the one on the left-hand side. Note that we have a sound absorption coefficient over here on the left-hand side, and it's right around 0.4. Now these are for materials that are all the same thickness, but they're different densities. But notice none of them are above 0.4. But as we get closer to 1,000, we see they're either around 1 or even slightly higher than 1, and we'll explain that in a minute. But what we're seeing here is that as we get higher up in frequency, our material is a better absorber. And part of that's a function of thickness, but lower frequencies have much longer wavelengths, so it's a lot harder to dampen those low frequency sounds. The analogy, I think, is anybody that's been driving around and they pull it next to somebody who has their radio playing loud, you'll roll up the window, it gets rid of all that high frequency screechy sound, but you still got all those bumps and thumps that still come through. So that's why it's so hard to deal. That's why you still hear those, is because of those long frequency noises. But if we look at the plot on the left, this has to do with density. So note that we have a 4-pound product, which is the bottom curve, that yellow one. And then as we go up, we get increasingly dense. So, and it also increases our low frequency absorption. But notice once we get to about a 12-pound per cubic foot density, we have this drop down to 0.8 at about 500 hertz. And the rest of that line is below 1. Even though it still performs well, but it tends to be more reflective the denser that it gets. And that intuitively, that makes sense. Now, if we go to the plot that's over the right-hand side, this is sound absorption as it relates to thickness, and thickness is a big driver here. So if you look at the bottom line going up, you'll see it, and this happens to be our fabrication board. We offer it in a 1.1 5/8-inch thickness. You see that we start our NRC value below 0.2, but as we add an inch, we go to 0.3, and as we add another inch, we go to 0.5. And then if you look at these two top lines, that's actually an R19 unfaced metal building insulation. And again, even at very low frequencies, you have really good absorption. Again, going back to that frequency, the thicker it is, the better we are at absorbing. And also notice that once we get around 500 hertz, we're pretty much absorbing all the sound that hits that. The one thing I do want to point out, though, is you see this red line here where it kind of trails off and goes down. That's a product where it has a metal building facing on it. And so it's a poly scrimcraft, or similar to an ASJ, or maybe a foil type facing, something that's fairly air impermeable. And you see we have good absorption at low frequencies, but we reflect sound as we go higher up. So that's something to keep in mind. A lot of times you'll see people wanting data that for sound absorption for pipe sections, but then you end up putting a metal jacketing on it, so your absorption is not going to be that great at higher frequencies. Fortunately, those higher frequencies are much easier to attenuate or cause them to diminish. Okay, next slide, please. Okay. Now we're going to talk about is sound transmission. So we talked about sound bouncing off of things. This is sound actually going through things. And how we run this test, essentially you have what we call a source room and then a receive room, and then you build this partition that you see here that's in the magenta that's right in between those two rooms. All we do is turn on the sound in the source room, and we measure the source and the receive room simultaneously, and we're just trying to determine how much sound that wall blocks. Now, roughly speaking, you're looking at an STC50 wall is going to roughly block 50 decibels at 500 hertz, and that's what's coming through that partition. Again, as with NRC values, we like to have a single number so we can compare it to other wall construction types, or if we're looking at NRC values, we want to compare that to other materials. So rather than compare every sound absorption coefficient in every at every frequency, it's much better to just have a single number to make comparisons with. Next slide, please. Okay, so now that we've taken a look at transmission loss and how much sound we've blocked as it's going through, we go on to insertion loss, and what we're doing here, if you look at the diagram below, that kind of parallelogram, well, I'm sorry, not parallelogram, this polygon, I guess. Kind of the thing here is you don't want to have two parallel walls, so you don't have any standing waves bouncing around. But what you do want to do is, or what we're seeing here, is a pipe that's running through this room, and that little box in the upper left-hand corner labeled 1, that's a speaker. We're running it in this pipe, and we're measuring how much sound is radiating off of that pipe. So, and actually the term is sound power. What we do is we run the same test over again, but after we put insulation and jacketing and some other kind of dampening materials on it. And so what we're looking there at is the difference in sound coming off the pipe before you put the insulation on and after you put it on. Or think of it this way: after you inserted the insulation, this is what that final performance is going to look like. Let's see. Now, this is not to be confused with, there is insertion loss used with things like duct liners and things like that, and that's actually sound traveling through the duct from the fan source to wherever the end is, and maybe that's the room. That's one kind of insertion loss. This is another type, which is more like sound transmission loss that we talked about in the previous slide. Next one, please. So we talked a little bit about single number systems, and the STC, we're always trying to get that to plot to a reference curve. And then we give that a number that kind of fits that curve. In this case, we have a ISO 15665, and what this does is this actually gives us a whole spectrum that we have to meet. Now, one of the problems, or one of the challenges with pipe acoustics is you have this this thing with diameters and geometry that you have to think about. So if you have a much smaller pipe section, and let's say it's 8 inches in diameter, you have a lot more insulation over a given area than you do if it's a 36-inch duct. So there's actually more material per area, so it does a better job of blocking sound. The other thing is, if I'm trying to reduce the noise level a certain amount, rather than having to test everything, it's a lot easier to just have some criteria in order to do this, and that's what the ISO 15665 gives us. It narrows all those selections down to 3 different pipe sizes. So you have pipe size 1 is for diameters less than 11.8 inches. Pipe size 2 is that range between 11.8 and 25.6. And then if you go to pipe 3, that gives you between roughly 26 inches and 39.4 inches or a meter. So you have 3 different pipe diameters. So it takes that geometry out of it. And then it gives you 2 insulation thicknesses. And it's pretty much going to be either 2 inches or 4 inches, depending on what you're doing. And then 4 weights of jacketing and lagging. So it sounds like there's a lot of combinations, but if you look at the table that's over in the upper right-hand corner, you see that we have, if you wanted to get a Class A, you can do what they call a prescriptive type of assembly where if you follow these requirements where you have a porous layer that's 50 millimeters thick and that you meet that stiffness requirement for insulation, and then mass per unit area, and this is an important thing. That mass per unit area is actually, that's going to be your jacketing and maybe a mass layer if you're using mass loaded vinyl. And one of the ways to think about this is that if you have sound inside that pipe and it's traveling out, you can almost think of that as like a curved wall section where one side of that pipe is going to be one side of the wall, then you have insulation, then you have jacketing, which you could think of as the other side of that wall, and that's maybe the easiest way to think about it. Now, one of the ways that we improve that is we have to improve both thickness and usually adding a lot of weight to something. And that works to a point. We'll see that on the next slide, but for now, it's just important to note that we start at 2 inches, then we go to 4 inches in thickness of insulation, and everything else is kind of driven by how much mass that we put into that system and where we're putting it. In the lower right-hand corner, where we're going to end with, is the nice thing about this standard is it gives us at least A, B, and C. D was one that was created by one of the largest oil and natural gas producers as to kind of give enhanced capabilities. But if you look at this, you see that if the bottom line there is going to be A2, and so if as long as your tested assembly is equal to or greater than that line, then you meet that requirement. Or if you meet a B, that means you also generally meet an A. So, and so on and so forth. So as you keep increasing your performance, that means you pass all those other subsequent levels as you're going up. Next slide, please. And so maybe just a note here, so I said earlier that if you're looking at a system, ideally you want to have mass and thickness. So what you want to have your mass in the pipe, and you want to have your mass in your jacketing and any kind of lagging that you're using, but you don't want to have a lot of mass or compressive strength in your insulation. And here's a point that illustrates this. If you look at the table on the left, this is a comparison of a 2-inch product and they're both 2-inch products. One is an 8 pound per cubic foot density. The other one is 11.25 pound per cubic foot density, and they're both mineral wool products. But you can see the lighter density product performs considerably better than the high density product does, and ranges anywhere between 5 and 10 decibels as you kind of look at the difference between those two graphs. If you go over to the graph on the right hand side, you can see that there's a considerable difference, and this is just a 4-inch product. And again, these are both products with the same density, and we have as much as a 15 decibel difference here at 2,000 hertz. So that's quite a bit different. The other thing about this ISO standard is it has a requirement in there for density, which we know it's just a volume over or a mass over volume. But then you also have airflow resistivity, and that's how easily air passes through the material. So if it passes easily through, it's a good sound absorber. As you get too dense, it tends to impede that airflow and tends to be more reflective, like we saw on that 15-pound board earlier. The other way to look at this is you can also do a performance-based, and that's where you actually test all these configurations. If you remember on that table that we had on the previous slide, it tells you what components you need to meet a certain specification, so that's prescriptive. However, if you wanted to value engineer that and maybe take some thickness out of jacketing or some of the mass loaded vinyl, you could certainly do that and still pass the test. But that's kind of a known thing that if you do that, you will get the results that you're looking for. Next slide, please. So looking at this, again, we said it's similar to a wall assembly, and it's about the insulation thickness, and it's also about the weight of the mass. So if you're kind of looking at these systems going from left to right, you have a Class A system, and that's going to be 2 inches with minimal amount of jacketing. Your next iteration at Class B is going to be 2 layers of insulation, and again, some type of jacketing. But Class C, this is where you start to see, and again, this is you can see the design details in the images below. The classes here, you can see that we start to add mass-loaded vinyl or maybe thicker and heavier jacketing on the outside of our insulation system. And again, if you think of this like a wall, that's more like a drywall component where you're adding mass. Again, you're increasing thickness of insulation, but not density. And finally, when you get to Class D, you're actually adding mass loading between the layers of insulation between your inner and outer layer, and then possibly adding 1, 2, or even more layers of mass loaded vinyl underneath your jacketing. So again, each one of those, has different performance levels. Okay, next slide, please. So, we've kind of gone through all this, and I guess the question on some people's mind is, that's great, so now what do we do with that? This is how a designer would look at this information. First of all, they would look at the spectrum that we saw early on in the presentation, and they would say, I'm looking at a fan or a pump, and I need to make sure that it's much quieter than what it already is. So we look at our spectrum, we figure out where our noise is being generated, and let's just say we have a 20-inch diameter pipe. We're trying to find out something that's going to have the most reduction at that frequency. And so if you look at that table at 500 hertz up in the upper right-hand corner, you see that we don't have a big difference. We're looking for something that's going to be 10 decibels or higher. We want to make a significant impact in that range, or something that's going to be considered to be half as loud. So if we look at construction C2, we can have a 14 decibel reduction even in just that frequency, which is going to help dramatically, particularly with this particular piece of equipment. And so what they'll do is the designer would specify at least a C2, maybe even a D2, but even the D2 doesn't give you a huge increase over what you get with C at that frequency. And that's what they would do. So they would specify, just make sure that it's C2, which 2 inches is going to be the pipe size, and then C is going to be the performance level. And finally, if you look at the lower right-hand table, I think this is very telling. As you just pick a frequency, and let's look at 500 hertz. We don't see a big difference between A2 and B2 going vertically. There's only maybe a 4 decibel difference, so it's barely noticeable. But look, even if we go to C or D, we jump up to 14 or 15. So that's significant, and that's something we're going to perceive as being considerably quieter. And again, if you look at 1,000, 2,000 hertz, you see big differences as you go through those increments, going from A to B, B to C, and C to D. But notice as you get to 4,000 and 8,000, those differences get less and less. And by the time you get to 8,000, really, if it's a 4-inch system, it's going to perform pretty much the same. But if it has 4 inches of insulation on it, even though you might have a lot of mass in the form of jacketing and vinyl and things like that. Okay, next slide, please. So one of the things that we did at Owens Corning is, we are accredited to do ASTM E1222, which is a insertion loss test. But what we did is we went to an outside lab, and we went to Bojanica, Poland. Again, my apologies if I mispronounce that. But they, the Greifeld lab there, and they did this testing for us. So we have a lot of different combinations that we use, either pro section or industrial wrap, and we also have configurations with aluminum or stainless steel jacketing, depending on what your application is, and also covering all performance levels going from A to D2, from A2 to D2. So we cover that entire spectrum. This information, by the way, is on our website. So if you want to go look at some of those details, that's where you'll find them. Next slide, please. So finally, here's some of the foam glass things that I told you about earlier. If you look, notice that we have, start with the left-hand side. This is the D class, and we offer this one with our Pro section using these thicknesses, 50 millimeter and 60 millimeter. And then we have 1 layer mass loaded vinyl between the 2 layers, and then 2 layers of mass loaded vinyl on the outside to get you that D2 performance. Looking over at what we have for foam glass, notice that there's you have the foam glass core there, and of course, foam glass is just an incredible product for any kind of low ambient conditions, whether it's chilled water all the way down to cryogenics. But now we also have a solution, a non-combustible solution for those types of applications, and typically that'll be 2 layers of foam glass in the center, and again, we'll have to add mineral wool on the outside of that to get the performance we're looking for. Maybe one thing to note, because foam glass does have such a high compressive strength, it does tend to conduct sound more readily than a softer material like mineral wool. So, so it does take almost the same amount of mineral wool on this assembly to make sure you're meeting those acoustics, or those requirements. But again, you're going to have a non-combustible system when you're done with that. Okay, next slide, please. Okay, so we're getting to the end here. We're just going to kind of wrap a few things up, and we'll just kind of review what we talked about, and then also talk about some resources that we have available. Next slide, please. Okay, just a couple of things. We talked about the Owens Corning thermofiber industrial mineral wool product offerings and what we have in the form of water-resistant pipe sections, industrial board, and industrial wrap. We also talked about basics and thermal performance. We talked about noise level, the type of noise, and that's whether it's high frequency, low frequency. Talked about relative loudness, whether it's something's half as loud, twice as loud, those perceptions. We talked about NRC values. Usually for optimal absorption, you want something that's going to be 2 inches or thicker. It's going to cover it in most cases. If you have something where you have to absorb a lot of low frequency sound, then you have to go much thicker. As we saw, we might need a 6-inch thick product to really get a good absorption at low frequencies. We talked about sound transmission class. This is useful if you're doing enclosures for compressor stations. You want to look closely at STC values and make sure that if you have to build enclosures, you always want to make sure you have continuous wall elements. You don't have fans that are on the wall that's going to be facing the property line, because sound will go right through those. And those are topics for another discussion, but those are things you want to be aware of. Usually a direct line of sight is what you're looking for, so make sure you don't have any sources going directly from site to source. We talked about insertion loss, about thicker and heavier is best, at least with regard to jacketing and mass-loaded vinyl cladding, that kind of a thing. But again, you don't want to go real heavy and real stiff on the insulation itself. Mineral wool products that are around 8-pound density are optimal. Or if you have something that meets those prescriptive requirements that are in ISO 15665, that'll also work. And then finally, we talked about ISO 15665. There's a prescriptive method where it's just simply a matter of using the components that they recommend, or you can actually do the testing on an actual assembly. Maybe there's an opportunity to value engineer, or if you wanted to do a hybrid system like Owens Corning did with our mineral wool and foam glass, that's another way to make sure that you capture that and show that that's appropriate as well. Okay, next slide, please. A couple of things to point out. I'd like to talk a little bit about NIA. They have a lot of good information, not just for industrial applications, but also mechanical. They also provide training, guide specs, material specifications are a great resource, and they're geared towards industry. They're not a fiber-centric, foam-centric organization. They cover the needs of industry, and so they're great. I think it goes without saying too, and we hadn't talked about this, but any kind of system you put together has to be installed properly using the right materials and put together by competent help. And as long as your detailing is done right and you're constructing it properly, you can expect to get the performance that you designed into that system. I'd also like to point out we have these resources. We have the technical bulletin for the ISO 15665 acoustics, which we saw the table of in the presentation. We also have NAMA 3E Plus that also has pre-populated industrial products in it. So if you want to look at insulation thicknesses or for safe to touch or for process control, we also have that information there as well. Next slide, please. And then finally, we talked about NIA earlier, but one thing specifically that we want to focus on again is installation. They do have a certified thermal insulation inspector program. It's something they just came out with, and this is a great resource. So this will teach people to on what to look for, what should be done, what could be done, and just helps to maintain and the assets that you put so much thought and money into making it work. This will help keep that working much longer. So you have a much better performing and reliable system. Okay, next slide, please. All right, well, thank you so much. I appreciate your attention today. I'm going to turn it back over to Jared. If anybody has any questions, I'll be happy to answer those for you.
Thanks, Doug. This was really informative. Really appreciate you taking time today. We don't have any questions in yet while people kind of gather their thoughts and maybe get some questions entered. I'll go ahead and draw for the Amazon gift card. And let's see, it is Kevin Ray out of Kentucky. So Kevin, I'll reach out to you via email and let you know how we're going to get that to you. But so congratulations. And let's see, we do have a question. Oh, not a question, just a comment. It says thank you for the training. You're very welcome. And yes, Doug, thank you very much. We'll give it a couple minutes, but just to see if there are any other questions that come through. I do want to remind everybody that to stay in tune and updated with future topics and webinars hosted by DI through this webinar series, follow us on LinkedIn. We'll post everything there. You can also visit our website at distributioninternational.com. You can also check out our YouTube channel. If you go to YouTube and just search Distribution International, you can see some past webinars we've done and some other videos as well. Doug, I don't see any more questions, so I think that will do it. That'll wrap us up. Thank you, and also thank David Cox for sitting in just in case. So David, we appreciate you guys at Owens Corning for doing this for us, and wish everybody to stay safe, wash your hands, all that good stuff, and we'll see everybody soon. Thanks. Bye.
All right. Thanks, Jared.